Hello, dear student. Welcome back to our YouTube channel, School for All. I hope you are all doing well and preparing seriously for your examination. Today, I decided to work on further mathematics, more precisely on further complex numbers, to help all my further math candidates preparing for the GCE. Complex numbers are one of the most important and the most repeated topics in further mathematics. In this lesson, we shall look at the important concepts like De Moivre theorem, solving complex equations, transformations, modulus, and argument. My objective is to help you understand the method and the techniques needed to answer examination questions confidently and correctly. I also want to congratulate all students doing further mathematics because choosing further math already shows ambition and determination. Most students doing further mathematics usually aim for career in engineering, computer science, architecture, telecommunication, and many other scientific fields. So keep working hard and believe in yourself. I also want to remind you that for students who need orientation about engineering schools, concours preparation, or career guidance after GCE in Cameroon, feel free to contact me. Without forgetting medicine school also. I am Mr. Chube, the head of the engineering department at Confidence Corporation, a group specialized in concours preparation and career orientation. If this video helps you, please like, subscribe, and turn on the notification bell so that you do not miss the oncoming video. Thank you very much for watching, and let us begin today's lessons on further complex numbers.
Okay, students, so let us proceed with the sample DC questions. So here, this sample DC question, I'll use it to give the full correction. While doing the correction, you see that I'll do some recalls that will really help you. That will really help you to solve any other question concerning the specific question that I'm doing here. Exactly. So if you have the concept, when I'm solving, I will do the recall such that you have the concept to solve any other question similar to this one. So let us start with the first question, question 10A of the sample GC question. Okay, so the first question here is talking about using De Moivre theorem or otherwise solve the equation z square equals to 1 plus I. So using De Moivre theorem or otherwise solve this equation. Now let me give you a recall. Let me give you a recall that you people should master anytime you're having the equation of the form z to the power n equals to I plus ib. Exactly, where a and b belong to a set of real numbers. So anytime you're asked to find the n root of a complex number, anytime you're asked to find the n root of a complex number, anytime you're asked to find the n root of a complex number, this is what you're supposed to do exactly. Master this method and no question on n root of complex number will be more than no. The first step here, the first step is to express, you express a plus ib in polar form. When I'm saying polar form means in exponential form. So that is, you should put a plus ib in the form r e to the I theta, where r is called the modulus of I plus ib. In bracket is how we represent it, modulus, and it is equal to square root of a square plus b square. So there is it. And theta is the argument. Theta is called the argument of a plus ib, the complex number. Now, how do we find the argument of a complex number? Argument of complex is quite easy. It's okay. You should first of all know your quadrants. You should first of all know where my complex number is located on my complex plane. It's okay. So I know that what? If this is a complex plane, this should be what? This should be the x-axis represent our real axis. This should be the real axis, and this is the imaginary axis. It's okay. So for you to find the argument of a complex number, you should know where the complex number is found on your complex plane. So the argument of a complex number is the angle formed by what? The real axis and the complex number. So if the complex number is found in quadrant, the first quadrant, it means that here, you know, the complex number is maybe here. I can name it maybe this is the complex number z. It's okay. Z we coordinate I, we coordinate AB. Exactly. So you know that this angle now here is simply equals to alpha, and alpha is what? Tan inverse of B all over A. Is okay, and this value gives us directly theta. Yes. So when your complex number is found in the first quadrant, therefore the alpha, which is tan inverse of the imaginary all over the real, is simply give us the argument of the complex number. As I said before, argument is the angle formed between the real axis and our complex number. Now when it is found in the second quadrant, be careful. In the second quadrant, you see now, let's say maybe if this is a complex number here, you see that the angle formed is here. Is okay. You see that that angle can not be alpha directly. No, it should be. So the argument here theta now should be what? Should be pi. Should be pi minus alpha. There's it. Where alpha is tan inverse of b over a. Don't forget. You see. So when you relocate where the complex number is found in the quadrant, therefore you take down pi. If it is found in the second quadrant, you take pi minus the angle that you have calculated. Okay. So there is it. It means there is the angle between the real and the complex number z. Okay. Now when it is found in the third quadrant, you see now in the third quadrant, the angle formed now should be something like that. It's okay. That angle already is greater than pi. Are we together? So it means that the theta now should be what? Theta now should be negative pi plus alpha. Exactly. So let's say alpha minus pi, because that angle means that alpha already should be greater than pi. So when alpha is, look at that angle should be greater than pi, should be negative pi plus alpha. And the third and the fourth quadrant, let's see z here. You see that the fourth quadrant I can measure directly like this. When I measure now, be careful. When you measure that angle like clockwise, it means that alpha now will be negative theta. Normally angles are measured anti-clockwise. Exactly. Positive. So here, if I want to measure, the easy way for me to measure the angle between the real axis and the real axis and our complex vector z is to measure anti-clockwise. Is to measure clockwise, pardon. Therefore, by measuring clockwise, alpha is simply equals to negative theta. So that is the quadrant that you should master. First quadrant, alpha equals to theta. Second quadrant, theta. The argument theta is equals to pi minus alpha. Third quadrant, theta is equals to negative pi plus alpha, and so on. Okay, so that is what I wanted you to master. So you people should know how to find modulus and argument. You people did it in math already. So this is more recall for you to master the quadrants. Now, people should look up. When now you have the modulus and the argument, now apply the De Moivre theorem. The De Moivre theorem. Now, the De Moivre theorem says what? Anytime you want to find the n root of a complex number in the form like z to the n equals to where, when you have been written it already in the exponential form, n roots, z to the n means we are having how many roots? N roots is okay. So we are having n roots. It means that the map to you say you take zk. Yeah, to remove this n, you should do what? The n root of r exponential of I theta divided by n, but plus 2 pi k divided by n also. It's okay. So let me put it like that directly. Directly, since they have a common denominator. So I'll put theta plus 2 pi k all divided by m. So that is the math theorem. You people should cram it. Cram it, no need to understand. Now, where k here is the number of roots, it can go 0, 1 up to n. So it means that if I'm having 2 roots, k will take 2 values, 0 and 1. If I'm having 4 roots, k will take 4 values from 0 to 3. Exactly. So n here represents the number of roots. So k here is there to give us the roots. Now, why am I putting 2 pi k? 2 pi k is to have all the values of z. Exactly. So 2 pi k is to have all the argument, in fact, to generalize the argument, because we know that what theta, if I have maybe the first value of theta, it will repeat itself after how many? After even after whole numbers of pi here. So even numbers of pi, 2 pi, 4 pi, 6 pi, 8 pi, it will repeat itself. So that data will repeat itself, so that we should find what the different roots of z. So that is why you should cram. When you cram this, that is all. You can solve any question concerning n root of a complex number. Now let us come back to our question so that we should not waste time. Let us come back to our question. That was the summa recall. Okay, now coming back to our question, we are asked to solve the complex equation. Okay, so as I said, the first step I should express 1 plus I in polar form. So this is my first step. I will express 1 plus I in polar form. That is easy. It means I should first of all find the modulus. So the modulus of 1 plus I is simply equal to square root of 1 square, the real part square plus the imaginary part. The coefficient of I is what? 1 square. So square root of 2. As easy as that. Then I should find the angle alpha. I should find alpha. Another alpha is equal to tan inverse of 1 over 1, which is pi on 4, as easy as that. Now, let me locate my complex number. Positive means it's defined in the first quadrant, therefore, theta equals to alpha, which is equal to pi on 4. It means that 1 plus I is simply equal to root 2 exponential of I pi on 4. As simple as that. Now, it means that this is the exponential form of this. And I think people should know how to leave from exponential form to trigonometric form, therefore back to algebraic form. That is not difficult because we all know that one. Exponential of I, theta, is cos theta plus I sine theta. So from there you can change it to what? From there you can change it directly to trigonometric form, and then from trigonometric form you change it to algebraic form by simplifying the values of sine and cos. Okay, this implies that z to the power 2 will be simply equal to what? Square root of 2 exponential of I pi on 4. Then I apply now the Moivre theory. So applying the Moivre theorem, we have zk, applying directly, zk will be equal to square root of 2 to the power 1 over 2 exponential of I pi all over 4 plus 2 pi, okay, all divided by 2. Exactly. So here 2 takes the value of n. As I was saying, n equals to what? N here equals to 2. It means that k is going from 0 to 1. So I will start. My z0 is simply equals to what? You see that my z0 is simply equals to g is the same as 2 to the power 1 over 4. Yeah. So you know that square root is the same as 1 over 2, 1 over 2 to 1 over 2, 1 over 4. Exponential of I pi on 4. So this is the first value of z. Then z1 equals to, you can leave it like that, no need to change it to algebraic form. You can leave your answer like that if you want. Then the other z1 now will be 2 to the power half, 1 quarter, exponential of I pi all over 4. Pardon, yeah, these two will multiply here. So here will be 8. So these two multiply, I have 8. Then when k takes the value 1, I will have 2 pi. Exactly, 2 pi 2. We can say I will have 2 pi plus, I will have pi all over 4 plus pi, which is the same as 2 to the power 1 quarter exponential of I. Okay, here is 8 all over 8, pardon, because they say divided by 2 here. So pi all over 8 plus pi is the same as pi all over 8 plus 8 pi all over 8, making 9 pi all over 8. Since the power is n equals to 2, therefore we have two roots, z0 and z1. Okay, let us proceed with the next question of the sample. question. A transformation T, we're having a transformation T is defined by Z to W. It means that the transformation transforms Z to W, where W is equals to 3Z plus 4I all over Z minus 1, where Z cannot take the values 1. That is it. Z cannot take the real number 1, because if you take it, the image of Z is no more existing, because this is the object. Don't forget, this one is the object there, this one is the image under the transformation T. Transformation. So that is it. Now the first question, Roman 1. Find the invariant point of this transformation. Invariant point, easy. To find the invariant point, it means when I transform Z, is to have Z back. Invariant, it means that it does not change under the transformation. So it means that W is simply equal to Z. So the image is equal to the object. That is the meaning of invariant point. So having that in mind, we replace directly. I will have Z equals to 3Z plus 4I, Z minus 1. Is okay. Then from there, I should make Z the subject to find the invariant point. So I will have Z into Z minus 1 equals to 3Z plus 4 plus 4I. I will have Z squared minus Z equals to 3Z plus 4 plus 4I. Okay. I will have Z squared minus 4Z equals to 4I. I will have Z squared minus 4Z minus 4I equals to 0. Therefore, I use that is a quadratic equation. I'll use a quadratic formula to solve it rapidly. So quadratic is negative b, so it will be 4 plus or minus square root of b square, which is 16, minus 4ac will be plus 16 I square. Okay, I think is that, no, pardon, 16I. Okay, because it's 4ac, a is 1, c is negative, 4I will be negative. Then divided by 2, divided by 2a, a is 1, so divided by 2. So my z will be simply equal to, I will factorize 16, square root of 16 is 4, I have 4 plus or minus 4, square root of 1 plus I divided by 2. So I'll have simply z equals to 2 plus or minus 2 square root of 1 plus I. I think it's better for you to leave it like that, because to simplify it more will be difficult. So that is there's the Roman one of the equation. Now Roman 2 of the equation is, show that the image of the circle magnitude of z equals to 1 is a line in the W plane. So we want to show that the image of the circle magnitude of z equals to 1, the image of the circle magnitude of z equals to 1 is a line in the W plane. Now I think that some of you will be asking that, how come this is a circle? Yeah, in complex number, magnitude of all complex number equals to a constant forms what? A circle. Exactly. Like here, magnitude of z equals to 1 will form a circle of radius 1. Magnitude of z equals to 4 will form a circle of radius 4. Okay, so I will show you geometrically and algebraically how this forms a circle. Is okay. Let us show it geometrically. So it is let's say it's a small recall for you to understand how we describe this circle. Okay, now if you're having let's say my complex plane here is okay. This is the imaginary axis and this one is the real axis. Exactly. You see that it's like when you are describing the figure of an equation, it means that you are giving the locus of the equation. Yeah, you are giving the let's say you are giving the shape of the equation. Let's see the points that form the equation. How does it look like? How those points look like? So it means that z is any complex number written in the form a plus ib. Is okay. So and the magnitude of the z should give me 1. So the magnitude of any complex number should give me 1. Therefore, it means I can take here, can be Z. It can be Z, A plus IB. It can also be Z here. Make sure that the distance, because magnitude is what? The distance from the center to where? That is the modulus of a complex number. When you're calculating the modulus of a complex number, you're calculating the distance from the origin to where point Z is. Is okay? And that modulus should give us 1, should give us 1, should give us 1. That modulus should give us 1. You see that this forms a circle of radius 1. Exactly. It means that the set of points that describes Z forms a circle of radius 1. As I was saying, Z can have many points because A plus IB, A can take many values, B can take many values, forming what? A set of points. And those set of points, when it forms a set, when you join them, we combine those set of points, you see that what? We form the circle of radius 1. So that is how you can show it geometrically, how you can show that the magnitude of Z equals to 1 forms a circle. Is okay? So now let me show you algebraically how does it form a circle. Algebraically, you should know that if I say Z, if I say that Z maybe is X plus IY, you see that what? Magnitude of Z is simply equals to X square plus Y square. It's okay? And the square root of that. And we know that the magnitude is equals to 1. It means that when I will square both sides here, so that I will have X square plus Y square equals to 1 square. Therefore, you see that what? The set of points that describe this equation Z equals, the magnitude of Z equals to 1 forms what? Form a circle of center 0, 0 and radius 1. Form a circle of center 0, 0 and radius 1. So there is it. This is how you can show it algebraically, and we did already how we can show it geometrically. Now, we now say that we carry now this circle, we put inside the transformation, we obtain now a line. So how can we show that? Okay, let us see how we can show it algebraically. It means that I will come here, I will try to come up with an expression in terms of W. It's okay? So I'll try to come up with an expression in terms of W. So to do that, I'll first of all, I'll come up with an expression in terms of W. From there, I will deduce. We all know how an equation of a line looks like. It's okay? Then from there, I will deduce that equation forms now what? A line. Okay. So the first thing to do here, come up with an expression in terms of W. I'll have Z minus 1 into W equals to 3Z plus 4i. Okay, it means that from here I will make Z the subject, therefore I will apply this condition, magnitude of Z equals to 1, and then come up with the expression in terms of W. So this implies I will have ZW minus W equals to 3Z plus 4i. Okay, then here what is common? W, no, I'll bring like terms together. I'll bring ZZ together since I want to make Z the subject. I'll have ZW minus 3Z equals to 4i plus W. Z is common here. I'll have W minus 3 equals to 4i plus W. Divide both sides. I'll have Z equals to 4i plus W divided by W minus 3. Now, I know that what, but magnitude of Z equals to 1. This implies magnitude of 4i plus W divided by W minus R should give me 1. So this simply means 4i plus W, modulus of that is same as modulus of, can call that, modulus of W minus 3. So you can see that this is an equation of a line. This is an equation of a line. So the geometrical interpretation of this equation is that this is an equation of a line. It means that W, that the set of points that forms W describe what? A line which is the perpendicular bisector of the line formed by 4i and negative 3. So you should try to understand this. I will show you after. It means that for me, I will say that what? W forms, therefore W forms a line. Therefore W forms a line. Now let me show you why I'm saying that W here forms a line, and that line should be the perpendicular bisector of the line formed by the point 4i negative 3. Okay, let me show you something. Let's say I consider a complex number z. It's okay if I write something like this. If I write the magnitude of z, any complex number z minus another complex number, maybe za, should be equals to z minus another complex number zb, yeah, any point of the complex plane. You see that what? Here, if I want to describe this equation, I will say that z is a line, or the set of points that form z is a line. The set of points that form z is a line because I'm saying z can take many values. It's okay. Z is not a point. You can think that z is a point. No, z is a set of points because z can take many values. So we can, let us say it like this. It will be better. The set of points that form z, the set of points that forms the set of points that form z describe the set of points that form z describe a line that divides the line segment AB into two equal parts. In simple English, it is the perpendicular bisector of the line AB. Exactly. The perpendicular bisector by the line formed by the points ZA and ZB. ZA and ZB are points. Yeah, they are points. The Z here is a set of points because Z can take many values. Z is a set of points. Yeah, it's a complex number formed by a set of points. Okay, now, so that is it. That is the geometrical interpretation of this equation. It means that when you're having any equation where there is Z here and there's a point here, so Z minus a point means that Z is a perpendicular bisector of the line formed by these 2 points A and B. Okay. That's what I was trying to say. It means that what? Let us consider one of the point. Let us consider that one of the point of Z is maybe M. So let one of the point of Z. Let one of the points of Z be M. It means that what? The magnitude of M minus ZA equals the magnitude of M minus ZB, means that, let's take this point B. Okay. When you're doing the modulus, you're finding the distance. It's okay. It means that this, like, find the distance AM equals the distance BM. Exactly. This is finding the distance AM equals the distance BM. Now it means that if I have a line segment like this, A, B, if AM equals to BM, therefore M should be the midpoint. AM equals to BM means that therefore M should be the midpoint. I want to consider those vectors. It means that what? M is one of the point of Z. That was one of the point. If one of the point of Z already is what? The midpoint of AM, of AB, therefore the set of point of Z, that is, it will be like this. The set of point of Z now will be on the same line, therefore the set of point of Z now will be a line that cuts AB into 2 equal parts, therefore it will be the perpendicular bisector of the line segment AB. So I hope you understand what I'm saying. Okay, so here, that is what I was saying. So this is the generalized form. Anytime you are seeing this type of equation, you should describe Z as what? A line. And that line is what? The perpendicular bisector of the line formed by the points ZA and ZB. Yeah, because when I take one of the points of this Z, that point is what? Is the midpoint of AB. Therefore, it means that when I take now, I will combine now all the set of points that describes Z. It will form now what? This is it. It will form now a line that cuts AB into 2 equal parts. So that is what I wanted you to understand, how this thing is interpreted geometrically. So let me generalize it. Now let me show you it even algebraically for you to see it very well. Let us do fast. The magnitude of W plus 4I equals to W minus 3. We are here. It's okay. I was just showing geometrically how this forms W forms a line. The set of points that describe W forms a line. Now let me show you. If I say that this is x prime plus iy prime, yeah, placing W equals to s prime plus y plus iy prime. So the image of z, which is x plus I prime. So the image will be prime prime. You see that when I substitute here, I'll have magnitude of W plus 4I will be simply equals to what? It will be simply equals to x prime plus I. I'll bring items together, the I together, I will have 4 plus y prime. It's okay. So now applying magnitude here, applying magnitude, the modulus value here, you come out with x prime square plus, when I will square this one, I will have 16 plus y prime square plus 8y prime square root of that. Okay, I'll do now same with w minus 3. You see that w minus 3, we simply have what? We simply have, let me put it there, I will simply have x prime minus 3 plus iy. When I apply the magnitude here, I will have x prime square plus 9 plus negative 6x prime plus y prime square root of that. When I equate the two, you see that the square will cancel. I will stay with when I equate these two, the square will cancel. I will stay with x prime square plus 16 plus y prime square plus 8y prime equals to x prime square plus 9 minus 6x prime plus y prime square. Y prime square cancel y prime square, s prime square cancel here. You see that we will come out with an equation of a line. Yeah, if I bring like them together, you see I will have 8y prime here. I will have 8y prime here. I'll bring this one here plus 6x prime. Then 16 minus 9. I'll have 16 minus 9, which is 7 equals to 0. This is the equation of a line. See that the set of points that forms our W describe what? A line. So there's an algebraic proof. Now in the exam, no need to do all this. In the exam, when you reach here, you can conclude that W forms a line in the W plane. As easy as that for me. Because here the interpretation, yeah, the complex interpretation here is that W forms a line. So from here already, from here, yeah, you can conclude. I wanted you to show you algebraically how this forms a line. Okay, so let me put the general form here so that you should not forget. So the small recall here is that anytime you have an equation in the form z, modulus of z equals to a constant a, therefore where a is a constant, a is a constant instead of real numbers, therefore you conclude that what? Therefore you conclude that z forms what? A circle of radius a. That's it. Anytime you have an equation in the form z minus maybe another complex number that will call maybe I don't know, let me call w equals to, let me za, z minus another one zb. When you have an equation in this form, from here you can conclude that what? Z forms what? A line. It's okay. From there you can conclude that z is a line. Z is a line. So that is the general form that you should know. But you're saying that z bar is a conjugate of the complex number z. So we know that z bar is a conjugate, and that z bar equals to, yeah. So this is one of the properties of conjugate of a complex number. It's easy for you to prove this one. You can be asked to prove it in the exam. To prove this equation, it's easy. If I say that z is equals to let's say a plus ib, comma, it means that z bar should be equal to a minus ib. You see that when I will multiply the two, I will simply have a plus ib into a minus ib. I will all know that what a plus ib to a minus ib is simply a squared plus b squared. We know it now because I squared is what? I squared is negative 1. So you should know it. And we all know that what modulus of z modulus of z will be square root of a squared plus b square 1. Will square both sides. If you remove this, therefore it is a plus b. Therefore that equation is therefore the equation is the same. That is it. The right hand side equals to left hand side. No. So they gave it inside the exam, so no need to prove it again. And then given that modulus of z minus 3i equals to modulus of z minus i. Given that modulus of z minus 3i equals to modulus of z minus i. Roman 1, show that Roman 1, they are asked to show that the conjugate of z can be written as z minus 4i. Show that the conjugate of z can be written as z minus 4i. Okay. So we have to use this equation given and this property. Okay. So from here, I'm having modulus of z minus 3i equals to modulus of z minus i. Now, for us to remove this modulus, we all know that we will square both sides. But I know that what? If you remember, when I'm squaring the modulus like this, it's simply the same as doing z times z bar. So I will apply it here directly. So the modulus of this square is the same as doing z minus 3 times z minus 3 bar is what? Is z bar plus 3i. I do same on the other side. Z minus I, z bar minus I. Okay. Then let us simplify very fast. I will have z bar plus 3z I. Okay. Then minus 3z bar. Negative 9i plus 9i. I think is it now? Z bar 3zi negative 3z bar, pardon, there's I here, then it will be negative 3i square will be okay. Negative I square is negative 1. So that's it. Should be equals to, I do say me, I will have z bar minus I z. Okay, z bar minus I z minus I z bar, then minus 1. Okay, now I think here should be plus. The conjugate of this one should be plus. Okay, so here will be plus 1. Okay. So I will have this one, I will have 3zi. When I bring this one here, I'll have minus iz minus 3z bar I plus iz bar plus 9 minus 1 equals to 0. So this implies 2z I minus 2z bar I, then plus 8 equals to 0. Okay, I bring the now I have negative 2z bar I equals negative 2z I minus 8. Okay, I will divide both sides by negative 2. I'll have z bar I equals to z I plus 8. I divide both sides by I. It cancel. I'll have z bar equals to I cancel z. Then here will be 4. I will divide by 2 here, we cancel here. 4 times. Okay, the negative cancel, I'll have plus. Okay, so here I'll have plus 4 all over I. Now this I, to move the I in the denominator, I'll multiply top and bottom by I. We are doing the conjugate. I'll have z 4i, I times I is I squared, which is simply equals -1, so I'll have -4i. So there is a proof. Okay, so there is a proof for question B, Roman 1. Let us go to Roman 2. Roman 2 of the question. Wait, there was a hence. Okay. When you are just from proving that z bar equals to z minus 4i, they say hence deduce that z can be x plus 2i. Okay, now the only way for me to come up with x here is to let z to be equal to x plus iy, any complex number x plus iy. So this implies z bar will be simply equal to s minus iy. It's okay. Then I will carry this, I will substitute the 2, substitute in z bar equals to z minus 4i. So this implies I will have x minus I, y equals to x plus I, y minus 4i. X cancel with x. When I will have negative 2i, y equals to negative 4i. So this implies I cancel here with I, negative, 2 here 1, 2 here 2. Y is simply equals to 2, therefore z can be written as, I'll come back here, I'll substitute now the value of y here. So z is simply equals to x plus I2 or 2i. Yeah, it's 1 or 2i. So there is the value of z. Yeah, we already have the imaginary part. Value of y, let us see how we can do Roman 2 of the equation. If they are saying that if the argument of z is equal to theta, find the range of values of theta. That is all. Now I know that z equals to x plus I, y. That is it. And I know that to find the argument, I should first of all know the angle of z. Then I should know also the position where z is found on a quadrant. It's okay. If you remember, this is the quadrant, imaginary real, exactly here. Alpha equals to theta, which is equals to tan inverse of y on x. In fact, let us say theta equals to what? Alpha. Is okay, this first quadrant. Okay, for second quadrant, we all know that what theta equals to pi minus alpha. So let us first of all calculate alpha here. Alpha here is simply equals to tan inverse of y all over x. So it's the same as tan inverse of y is how many? 2 all over x. Now, look at z here, x plus 2i, okay, the value of y is 2. Z here, we should now go and look where z is located on our quadrant. You see that the imaginary part is already positive, it means that I'm already on top here, but I don't know for the real part. Yeah, because x belongs to a real number, it can be positive and negative. Is okay. So it means that for alpha, it means that z can be in the first quadrant or in the second quadrant. Is okay. So it means that for the first quadrant, I will simply say that what? I will simply say that first quadrant alpha. You see that alpha, the range of alpha is from 0 to what? To pi on 2, because first quadrant is from 0 to pi on 2, to pi, then here to 3 pi on 2, then here to 2 pi. I think something like that. So for the first quadrant, we have this. For the second quadrant, alpha is greater than pi on 2, but smaller than what? Smaller than pi. Is okay. So that is the range. Now look up. But I'm looking for the range for theta, not for alpha. Together, we are looking for the range of theta, not for alpha. Okay. It means that for this one, for the first quadrant already, theta is also having the same range. Is okay. That's for theta. Then for the second one, I should manipulate here so that I should come out with pi minus alpha so that it should represent what? Theta. So first of all, multiply by negative. I will have negative alpha. Here will be what? Negative alpha here will be greater than negative pi, and smaller than negative pi all over 2. Then I add pi all 2. I'll have pi plus negative pi. I'll have 0 greater than pi minus alpha less than negative pi all over 2 plus pi is the same as pi all over 2. Yeah, same as pi all over 2. So theta is greater than 0, less than pi all over 2. You see, I'm still on the first quadrant. So that is it. It means that for the first quadrant of alpha, I'm still on the first quadrant here. So therefore, theta equals to alpha. They are having the same range. So that is it. And for it means that this implies that x is truly greater than 0. Yeah, because if theta is equal to alpha, because they are having the same range, and it's possible only when we are on the first quadrant. And if we are on the first quadrant, it means that the real part is positive, therefore x should be greater than 0. That is the condition. So from there we can conclude that therefore the range of theta is greater than 0, less than pi over. So showing that it is found in the first quadrant. Okay, showing that it is found in the first quadrant. Now next question. And hence, so there's an and equals to, okay, Roman 3, we are asked to deduce that z can be written as the form 2 quote theta plus 2i. We all know that what? We all know that what we know from the range is that alpha equals to theta and that x is truly positive. Is okay. So if I have z equals to x plus 2i is okay. It means that theta will be simply equals to alpha, which is simply equals to tan inverse of what? 2 all over x. Is okay. Yeah, I think it means that theta equals to tan inverse of 2 all over x, which is the same as tan theta equals to 2 all over x. So this implies if I want to make x a subject, I will have x equals to 2 all over tan theta, and another 1 all over tan theta is what? 1 all over tan theta is cot theta, so it will be 2 cot theta. Therefore, z can be written as 2 cot theta plus 2i. That is the proof. The next part of the question, Roman 4, is saying that given that the argument of z all over z minus 4i give us alpha. Given that the argument of z all over z minus 4i give us alpha, Roman 4, show that z can be written as 2 quote in bracket alpha over 2 plus 2i. Now, people should look up. I want to show this, given that we have that. Okay, it means that what I know is that z is 2 quote theta plus 2i. Means that what I've changed here is that theta becomes alpha over 2. Okay, it means that I should come out with an expression of theta in terms of alpha. Is okay. There I can now substitute, and to come out with it, we should manipulate this argument from laws. I think we know the some small laws of argument, properties of argument is like indices. I will know that the argument of z all over z minus 4i equals to alpha is the same as finding the argument. The same as finding the argument of z minus the argument of z minus 4i, which equals to alpha. But I know that what? But I know that the argument of z is theta. Is okay. So now we are left to go and find the argument of z minus 4i. Is okay. Now to find this argument, I should first of all come up with the expression of z minus 4i. But I know that what? This is the same as finding the argument of z is what? Z is let me use this 1 2 quote theta plus 2i Yeah, I can use that one, or I can use yeah, let me use this one. Z is 2 cot theta plus 2i, then minus 4i is okay. I'll have argument now of 2 cot theta is the same as what? The same as 2 cot theta minus how many? 2 cot theta minus 2i. Okay, now find the argument of this is the same as doing tan inverse. Yeah, if you remember, find the argument of 2 cot theta is the same as doing tan inverse of imaginary part, which is 2, all of our real part, which is 2 cot theta. Is okay. Now let us see, because argument, we should know where the complex number is located. This complex number, let us see where it is located. Another part, cot theta, 2 cot theta is already positive, I think, yeah, because it should be in the first quadrant. Then negative, this one is negative, so I should be in the fourth quadrant, and in the fourth quadrant theta equals to negative alpha. So theta equals to negative tan inverse of y all over x. I'm in the fourth quadrant. So since I know that I'm in the fourth quadrant, why am I saying that I'm in the fourth quadrant? Theta here is between, as we came out with a range. Theta was between 0 and pi all over 2. Between 0 and pi all over 2, cot theta is always positive. Exactly. Between 0 and pi over 2, cot theta is always positive. Therefore, making the real part here to be positive, and it's the imaginary part which is negative. So when I have real part positive, imaginary part negative, I'm in the fourth quadrant, and in the fourth quadrant theta is what? Negative alpha. So I will come here, it will be negative tan inverse of 2 all over 2 cot theta. Okay, so it's the same as negative tan inverse of 2 cancel, 1 all over cot theta. Negative tan inverse of 1 all over cot theta is the same as 1 all over 1 all over tan theta, which is the same as tan inverse of tan theta. And tan inverse of tan theta is simply equals to, there is negative here, so tan inverse of tan theta will still be what? Negative theta. So it means that the argument of z minus 4i is simply equals to negative theta. I'll come and replace in this my s equation. I will have theta, I'll replace argument of this by negative. Theta equals to alpha. So now I'll have 2 theta equals to alpha. Therefore, theta equals to what? Alpha on 2. Okay, you see that by substituting the value of theta equals to alpha on 2 in this equation, what is the equation? In the equation, by substituting theta equals to alpha on 2 in z equals to 2 cot theta plus 2i, the proof will come out. Therefore, z will be equals to 2 cot alpha on 2 plus 2i. As easy as that. So that is it. Okay, then let us go to the last part of our question. Okay, hence of the find the n minus 1 solution of the equation. Okay, we should find the n solution of the equation z minus 4i to the power n equals to z to the power n. Okay, so I think it will be easier for us to use the otherwise. Yeah, because if I bring this one down here, I will have z minus 4i divided by z adding to the power n divided by z to the power n equals to 1. We all know that this is the same as saying z minus 4i all to the power n equals to what? Equals to 1. Is okay. And I told you that anytime you're having the n roots of a complex number, you should present 1 in what? In polar. The right hand side in the polar form. Now 1 in polar form is very easy. Yeah, because the magnitude of 1 is still 1. The argument of 1, the argument of 1 will be exponential of I what? Argument of 1 alpha here is tan inverse of imaginary part is 0 all over 1. Tan inverse of 0 is what? 0. first quadrant, therefore theta is what? 0, therefore here is 0. Is okay? So 1 is simply equals to exponential of I 2 pi k. Yeah, there's 1. Because as I was saying, 0 will repeat itself after even values of pi. Okay, it means that our z minus 4i all over z to the power n can simply be written as exponential of I 2 pi k, as simple as that. And then I use the math theorem. It means that here I will have z minus 4, pardon, z minus 4 I all over z is simply equals to exponential of I 2 pi k all over n. Then here will be what? zk. Knowing that now k can go from 0 to n minus 1 because we want n minus 1. So now here I will have zk minus 4i equals to zk exponential of I 2 pi k all over n. I bring items together, I will have zk minus zk exponential of I 2 pi k all over n equals to 4i. Zk, when I factorize zk, I will have z equals to 4i all over 1 minus exponential of I 2 pi k all over n. So there is the value, as easy as that. Yeah, the domain is that k should not take the value 0, because if k takes the value 0, exponential of 0 is 1, or 1 minus 1 is 0. It means that k should start as from, means that k should start as from 1 up to n minus 1, because even n minus 1, if I place n, k by n here, I will have what? K n will cancel. Exponential of pi, exponential of I 2 pi is the same as cos 2 pi plus I sine 2 pi, and cos 2 pi is how many? 1, sine 2 pi is 0, 1, 1 minus 1, 0, making the root to not exist. So n k should start at 1 and n at n minus 1. So that is the root of the complex equation is. Okay, students, so this is all about the sample GCE equation under further complex number. This part 1. Part 2, I will take more question talking about similarity transformation. That is also very important. Yeah, you cannot go in an exam or further math, you don't know similarity transformation. It means that you cannot answer complex number. You are going the exam knowing that you will not answer complex number. Yeah.